Hi, my name is Eric Torkin. I'm the executive partner for the analytics practice at Technology Partners Limited. Today, I'd like to share with you something that I find very powerful for the professional analyst, which are tools and techniques that allow you to make big decisions with little data. So, I have assembled these and put them in a presentation. I hope you'll enjoy it. Let's get started. So, the first thing is an overview. So, as I mentioned, we have four mathematical models that have been proven accurate over time. There are studies that say this. These models are known as laws. They're fairly well known. They're easy to apply. They are easy to perceive, and they help you answer big questions with minimal effort. So, why don't we take a quick second and figure out why you should care and what are these laws? So, why should you care? Well, here's a simple situation. You're an analyst. Your boss needs to make a big decision, an investment, a deployment, an allocation of resources, and there's very little time, as usual. And of course, your ass is on the line because you're the person being asked to provide insight. So, what do? Well, you go back to the simple things. So, some of those require a certain mentality, okay? And we're gonna do just like the Buddhists and have mantras or basic affirmations that will help us along the way. So the first affirmation is that your problem is not as unique as you think. Uh, I've been managing this practice for a long time, and in the 12 years that we have been doing predictive analytics work, what we have found is though every company is unique, the problems that they're dealing with are not. It's kind of like that book from Joe Campbell, The Hero of a Thousand Faces. You have certain story types, certain archetypes that come up all the time. In terms of predictive modeling, you're looking at portfolio problems, you're looking at forecasting problems, you're looking at financial problems, and things are usually quantified in the same way, either in dollars or some sort of scientific unit. So there is always somewhere to go for a problem. Well, I have no data. I don't have enough data. I'm not collecting the right data. Well, the truth is, you probably have a lot more than you think. And that's a good starting point. The corollary to that statement is you probably need less data than what you think. So you have more and you need less. So that's a good place to be. And of course, there is a useful measurement tool that is easier than you think. So there are techniques because your problems are not always that as unique as you think. There are a lot of frameworks which may be available to help you out. And what we want to do today is kind of cover a few. So the first one we're going to cover is the Pareto rule. So the Pareto rule is what you probably know as the 80-20 rule. So let's look into the history first, and we'll get back to that. So the history of it is that Vilfredo Pareto was an economist, and he was the first, if you want, data scientist. So he went and looked at data at a time when economics was more about philosophy. So he went to look at historical data on various cities in Europe, including Paris and in France and in Germany and Italy. And one of his first observations is that 20% of something would account for 20% of something else. But that first something was land ownership. So 20% of the land in Italy was owned by, 80% of the land was owned by 20% of the people. And he plotted it out and started exploring this. And he started looking to compare with these other countries and these other times, going back all the way to the 15th century, historical data. that was kept obviously by hand and in books, he looked at this and noticed the same pattern, the same power law. And this was very interesting. So no one really made a note of it until Dr. Joseph Juran, which is known as one of the fathers of modern quality thinking, along with Deming's. Well, he read this paper and he coined it the 80-20 rule. And if you were to plot it out, it follows a power distribution, which is kind of cool. So you can actually model this out as a distribution or as a curve. So what does it do for us? Well, anytime you need more bang for the buck, there are a lot of problems where you just need to prioritize action and to get results. When you look at arrival times, or you're looking at the various problems, or even which products sell the most or which clients are more profitable, Pareto analysis will be relevant. So it looks at analyzing broad causes of problems in quality, but also prioritize action on a management level. And it's a powerful communication tool. The best example Pareto could give, and I love this quote, is that he likens it to Noah. And he says, if you're Noah on the ark and you got too much stuff on the boat, what are you going to do? Well, you want to lighten up the load. So what he says is go for the elephant. And if you throw one elephant over, well, it's the same as throwing over cats, dogs, squirrels, chimpanzees, whatever you want. And you will do a lot less effort to get the same benefit. So as you can see, one elephant is worth a lot of other stuff. So as you said, if you find the elephant, you're going to be in a lot better shape. So that's a really novel and fun way of looking at it. But in practical terms, how do you do it? Well, you need to categorize stuff. So if you were looking at reasons why someone might be late to work, well, is it traffic? Is it he's sick? Is it because he woke up late? What are the reasons that are contributing to employee tardiness? Set those up as group items. Then you decide, which measurement is appropriate. So how many minutes late? What did it cost? So usually it's a quantity, frequency, time thing. You need to look at your time element. You collect the data. And then, of course, I really like working with pivot tables because it allows you to kind of dimension this stuff and look at this analysis under different guises. And then the charting piece we'll cover in a second, and you can read this on your own. But you always have to start with a table. So we did this in Excel. So what's the first step? Well, we collect the data. Okay, so we went out, we talked to our every time someone showed up late, we asked them why it was, and we document it. We put it into a data table over here. Then the next step is that we sort by frequency. And then we assign a percentage, and then we do a cumulative. And what you'll notice is that if you were to cover the first two items, you would cover 71% of all the tardiness by just dealing with these two things. So a traffic tie-up, waking up late, maybe flex time would work for that because you get your people to show up after the traffic, or when they get up more naturally and they leave later, which might be better for them. Family problems, unfortunately, there's not much you could do for that, but technically speaking, the first 80% of the issues are taken up by 50%, and you could say, so the Pareto relationship is not perfect, but it is indicative enough of what we're trying to do. And you'll always find this, that the first couple items account for most, and this is a long tail relationship. Then, if we were to take this and we were to highlight it and go into Excel and hit combo chart, you will get a chart with these categories. It will put this frequency and this percentage and this cumulative. But this percentage is going to look weird. So all you have to do is when you chart it, delete that data series by selecting it, hitting delete in the chart, and it's gone. And then you can have the conversation if, doing flex time would be a meaningful solution for this. The second law that I find absolutely fascinating is Moore's law. Now, Moore's law is basically an exponential curve. And it's an exponential curve we find in a lot of places where it's useful for planning. So Moore's law comes from Gordon Moore, who was the co-founder of Intel. He was a total engineer. And he realized that every so often the transistor capacity would double. And he had slated it at about 2 years. And this relationship held and holds all the way up till about, I'd say, 2011. And then what they did is they needed to add cores to allow Moore's law to continue. Otherwise, it would have petered out. But Moore's law, as an exponential rule, applies to a lot of different situations. We'll look at those in a bit. So if you were to plot transistor count against time on a log linear scale, you would get this. And if you were to do it on a non-linear scale, on a non-log linear scale, so a typical scale, you would get this nice exponential curve. This chart and this chart are the same. Where can you use this? Well, I'm a professional business analyst, and I've worked on IT projects where I needed to figure out what something's going to cost several years down the road, or what kind of hard disk space. So I'm looking to make a purchase today, but I want the equipment to last 4, 5, 6 years. I need to right size capacity. So that could be in terms of hard disk size, RAM memory, data growth. And then there's another kind of interesting thing, which is technology pricing. So it's the quality adjusted price of IT equipment. And the best, it's also known as Macron's Law, where Bill Macron, who was an editor at PC Magazine, quipped in the 80s that your dream machine will always cost you $5,000. And I would say that up until maybe 5, 6 years ago, that held true, and probably still does today if you throw in the screens and all the peripherals. But if the box itself, you can get away with it with a little less than 5,000. But what it meant is that your whatever capability you wanted would always be at the same price point. And 6 months down the road, though, what you were looking at previously will be cheaper, there is something that came to replace that item at the same price point. So very powerful stuff. If you want to look at some actual data to see if this holds true, we collect some pricing data from a gentleman who wrote a book called McCallum, and we plotted this data out. So we had the inflation adjusted price for 2016 dollars, and we looked at capacity. So we're looking at cost. So hard disk cost versus memory cost, and you will notice that they both follow an exponential trend with an R squared of above 97%. So in both cases, which is insane because that means it's a near perfect fit. So there's proof that you could easily extrapolate or fit a curve and use that to project forward. Now, how do you do it? Actually, you'd be surprised at how easy it is. So the first thing is you need to pick a starting point. In our case, because we were looking at hard disk size, we could have gone all the way down to 1957, but to keep things apples to apples, we wanted to look at PC hard disk size. So the first PC it was in the XT in 1984 with a 20 megabyte hard disk. The pricing information we got was about $2,400 in 1984. So the cost per gig would have been $120,000 then, or nearly over $500,000 today. And as you can see, the sweet spot for the hard disk progressively went down from to 40 gigs to 80 and so on. And you can see over here in the chart, the size per gig, the gigabyte size, which is the historical, and then where it went off is exponential, where here we're dealing in 20 terabyte drives by 2024. So in 2024, it would not be unheard of that you could go to Best Buy and get a 20 gigabyte terabyte hard disk for $100. Okay. And of course, if you were to look historically at hard disk pricing, it's been the sweet spot, the price point has been $100, give or take 20 or $30, either way, going forward, and that hasn't changed. Just like as a bag of chips has pretty much been $1 or $2 forever. And on the other hand, what you'll notice is that the cost in 2016 dollars has also followed an exponential curve downwards. So it's a very simple process to do. You just need to pick a starting point, find the pricing data, and then every 2 years you have the cost and you double the size. In practical terms, for those of you who had Apples like I did, and I was fascinated, I was wondering, well, my Apple II, how would it compare to my iPhone? So I looked it up, and someone did this really nice infographic. So in 36 years, so from 1977, so the original Apple II, which had like 16 kilobytes of RAM, has basically gone up by 1,300 times the clock speed, 262,000 times more RAM, and 380 times more pixel density. And if you were more of an Apple guy and you were using that for clones, right? So that would make you look at a Samsung. Well, you're looking at 525 times the clock speed, 265 times the thousand times the memory, and 32.4 times more pixels, which is pretty crazy. So that's Moore's law, and of course, we can fit this in our pocket, and this was a fairly robust machine. So you wouldn't have carried it in your pocket, maybe on your head on a platform, but nothing else. So that's what we call Moore's law, and this is how we've seen it. There is a similar tool called the learning curve, but it's different. So the learning curve, which is our third law for today, is based on the work of Hermann Ebbinghaus, which was a sociologist from the 19th century. But he never quantified it. The quantification or the mathematification of that principle happened when Theodore P. Wright, who was an aeronautics engineer, in 1936 was analyzing production costs of airplane wings. And he found this relationship, which could be explained as how much time do I save by learning to do a task more efficiently over time? So as I repeat something, I get experience and knowledge, and that allows me to be more efficient. By the way, the picture of this guy over here is T.P. Wright. Now, T.P. Wright was not the only guy to latch onto this. So Bruce Henderson, the founder of the Boston Consulting Group, did some research and realized that, just like Gordon Moore at Intel, that there was a production efficiency that could be derived by learning how to do things better. So as your volume, your cumulative volume would go up, the less it would cost you to produce each individual unit. Now, he brought this out that if you were further along a learning curve than your competitor, then your cost and your cost competitiveness would be much higher. And of course, if you wanted to stay that way, you would have to pass on the savings eventually to your customer. Otherwise, you'd be inviting lower cost producers to come and mess around with your business. So then that allowed to build portfolios of where you sat on various learning curves, and that eventually gave way to the Boston Consulting Group's matrix. So where does it come from? Well, Wright's learning curve, and there's another math, but I haven't outlined it here, which is Crawford, which is a little more conservative, but you'll notice follows more or less the same pattern, which basically starts with the initial cost to produce a unit, and then what is the learning efficiency over time, which can be estimated. So labor efficiency, method improvements, technology-driven learning, figuring out how to calibrate or use your equipment better, product redesign. So all these wonderful things can help you do something faster and quicker. And this is where you get this exponential curve again. If you were to do a log linear relationship, it would again look like this. And as we mentioned earlier, you could look at industry profitability, but you could also forecast what it might cost you to build something over time. And it can be estimated specifically to you. There are techniques for that. However, if you needed a rule of thumb, you could look up for the major industries what learning curves were available. So for shipbuilding, it's 80 to 85%. Repetitive electronics, you get a lot less benefit over time, whereas purchase parts is higher. So the volume and the amount of learning you can do is really specific to what you're doing. Now here, what they did is they estimated the learning curve for the Model T, and they saw that over time there was a 77% slope. Here are the formulas. Henderson also came up with his own version, which has been known as Henderson's law. But when you look at the math, it is very similar to Wright's model with a few differences. Whereas B is a log linear relationship, whereas A is the elasticity of the output. But otherwise, conceptually, these two techniques are nearly identical. If you wanted to set these up as cumulatives, okay, you can see that your total effort or your total cost over time can be forecasted. So this is a really useful tool for the planner. Okay, that brings us to our last technique, which is the confidence interval, which is maybe a law, maybe it isn't. But let's look into it, because in any case, as an estimator, this thing is really useful. So the history of confidence intervals, again, it starts a long time ago when Jerzy Neyman originally developed the idea of estimating these. A lot of times it's based on the normal distribution or a uniform. It allows you to make a quick assessment on populations using samples. The math is fairly accepted, and guess what? There are practical ways to use this, because unfortunately, when you're in stats, they don't give you a reason to want to know what a normal distribution is good for. I tend to remind people that intelligence is normally distributed. Take that for what it's worth. And of course, there is a way to do a mathless confidence interval that Doug Hubbard proposed, which he calls the rule of 5, which is really novel, and it allows you to get out of tight fixes when estimating. And generally, if you're estimating a business problem, you should triangulate, which means you should have at least several methods to compare against. And I have done this in the past, and this was one of them, and it proved to work fairly accurately. So before we get started, let's just talk about one of the easier methods that you probably learned in school and meant nothing to you, which is the normal distribution. A normal distribution is found everywhere. Errors, the height of children in classes, the size of pencils that have been sharpened, whatever you want that follows a process. Okay? So it's every data point is the product of a repeatable process. That's why you'll find the normal distribution a lot in engineering. You use it in forecasting because it's what they call the law of errors as well. So a standard deviation, and as I like to quip, I used to think standard deviation was a social condition until the age of 25. But really, what it means is that it's how much dispersion you have against the mean. So one standard deviation plus or minus, so the area is basically two standard deviations, would cover 68% of the population. Two standard deviations covers a little more than 95, and three standard deviations from the mean, okay, is 99.73. But you're going to look at me and say, Torquia, I still don't know why I should care. Fair enough. So let's take a practical example. So, okay, Smarty Pants, how do I use this? Well, the first thing to do is simplify and apply. Round some numbers up. So if we have an average and a standard deviation, which could be estimated or real, we can estimate a population from a sample. So I've given the formula here, but it's actually really simple. If you have a class of 5th graders, like these cats from the early 80s, okay, the average height is 5 foot and the standard deviation is 2 inches. So what that means is 70% of this group of people is probably between 4'10" and 5'2". 2 standard deviations, which means 19 out of the 20 students here will be between 4'8" and 5'4". And say we had 100, our class was 100 students big, or you wanted to have, total, something getting much closer to the entire population, which is 99.73. That means that's 4'6" to 5'6". So you'll notice that the differences are evenly distributed on both sides of 5 foot. That's how you use it. So now when someone says, well, there's a mean of this and a standard deviation of that, you know that 99 times out of 100, it means 3 times the standard deviation on one side, 3 times standard deviation on the other. Coming back to the rule of 5, there's a way of doing this which is a little different than using normal approximation. It's using a quick sample. So you remember when we said you have more data than you think? Well, have no data will still travel. So the rule of 5 works like this. It's based on using a binomial distribution. So if you were to, and I'll explain it in a few seconds, if you were to use that to calculate, how, your probability of certain events versus happening versus others, you can do it really easily. And if you take the simple case of 5, so you need to find out what are the commute times to get to work, and you need to build a model, or you're filling out a survey, and you need to do it quick. So you randomly, and I do mean randomly, and there's issues around that too. But if you were to close your eyes, take an employee list and go and pick 5 people or randomly, or put names in a hat and start picking them out. You pick 5 of them and you ask them, how long did it take you to get to work this morning? So one guy says, well, 15, the other guy 42, 22, 55, 35, etc. Well, that's great. Is that significant? Well, significant enough, because with 5 data points, if I truncate the lowest and the highest, the confidence interval left between them gives me almost 93.75%. It's pretty good, surprising. Now, we're not looking at the average being in there or the true answer. We're looking at the median. So that's a subtle thing, which means that, half the population could be above 1 and half the population below 0. It could be between, above 3. So this is something to keep in mind. But it's extremely useful, especially when you're combining it with some other technique. Now, to scale this, because you could ask more people and get and still maintain the confidence interval. So we've put together this calculation to show you how it works. So let's take the example of 5 again. So if I had 5, if you were tossing a coin, you have a 50-50 chance of 2 events. So either you get a heads or you get a tails. And if you were to get 5 tails in a row, there's a 3.125% chance of happening. And if you were to get all heads in a row, the same. So the likelihood of not getting all heads and all tails is 6.25%. And if you take 100 and you subtract these 2 events from the total pool, that's how we calculate the confidence interval. It's pretty simple math. However, when you start getting a little further along, there's a really useful Excel formula, which is the binomial range estimate. You can look it up in the stats functions. And it helped me put together this table. So if I had 10 sample points and I were to remove the 3 lowest and the 3 highest, it would give me a range of 4, and that would give me an 89% confidence interval. If I were to sample 26, I would remove the lowest 9 and the highest 9. It leaves me a range of 8, giving me a confidence interval of 92.4. So this is scalable, and you can bring this up higher if you need it. But the point is not to make this so big that you may as well do an actual data experiment. The point is when you have no data, can you sample stuff real quick and get something insightful from it? And having used the rule of 5 on multiple occasions, the answer is yes. The other thing that I've used is the normal distribution, and that too tends to work very well. The normal can be found almost everywhere in nature and in process. So if you keep that in mind, these are really powerful tools. So let's conclude. Henceforth, as a professional analyst, I will be able to focus action to benefit, quickly assess and prioritize action using the Pareto rule. And because we do that, we'll be able to pick the low-lying fruit, save a ton of money, and eliminate distractions when it comes to executing operational excellence. Predict technology requirements and pricing. So that's the Moore's Law thing. As you saw, very powerful, not so hard to use. The learning curve. That'll allow you to build a forecast and figure out if I build this new plant or if I launch this new product, what will it cost me over time? How does that relate me to my market, my competitors, etc.? And lastly, the one we just covered was how to quickly estimate populations and establish ranges for further modeling or discussion using either the normal or the rule of 5. So now we have 4 new skills on things that perhaps we knew and we forgot or we just learned. So I'd like to thank you for the time that you've taken out of your busy day to listen and try and appreciate this stuff. And if it's useful to you, I'm grateful. And if you do have questions, well, you should feel free to give us a call. My personal information is over here. So I'm the executive partner. You have my email and my extension, or you can just call our general number if you want to look at stuff. We offer training, and we are Oracle partners, Palisade partners, and we resell over 15 analytics solutions. So either we can help you use it, we can help you learn it, or we can help you solve your problem. Again, thank you very much and enjoy the rest of your day.